So for this question, we've got a couple saved for their retirement by making the same monthly payments for 20 years into an account that earns 4.2% per annum compounding monthly. So that doesn't really tell us much about what to do just yet, but because they're saving for a retirement, I'm instantly thinking it's going to be a deposit annuity. So if we keep reading, at the age of 65, the couple retired and used all of their savings to purchase a perpetuity with an interest rate of 5.76% per annum, compounding monthly, paying $3,600 each month. We need to find out how much did they save each month to prepare for retirement. So what we have to do in this situation is we've got to start backwards. We're going to start with the orange text, and then that's going to help us to figure out how much they had to save each month, which is what was missing in the blue text. So step one, we're going to find the total value of the perpetuity. That's the perpetuity formula. In this case, we can rearrange it to find the perpetuity amount. And substituting the values, we've got 3600 divided by the interest rate per compounding period, and that gives us 700,000. So now we're going to use that 750,000 amount, and we're going to look at the blue, and we need to figure out what the monthly payment would have been in order to get an annuity of 700,000. So like I said before, we've got an annuity that's going up, so we're going to use this formula. I, for the first part, the blue part, is 0.042 divided by 12. Because it's a 20-year savings plan, we've got 20 times 12 is 240 for N. And then A is equal to 750,000. Plugging all of those into the equation, we get this. Now we've just got to solve for M to find out what monthly payments over 20 years would get them to have 700,000. So moving that entire bracket over, we've got to divide. And this is where, remember, to avoid errors, it's good to do this calculation in small chunks. So you'd enter the numerator first. Then once you've got the answer to that, you can enter that in second. And then finally, you can do 750,000 divided by the answer. When we plug all of that in, we get a monthly amount of 1999.28. So therefore, to answer the question, we could say, therefore, they saved $1,999.28 each month to prepare for their retirement. Next question, we've got Joe contributes $2,500 per quarter to an annuity, earning 3.6% per annum compounding quarterly. All right, so she's contributing money into an annuity that's going to be going up. So we're dealing with an annuity here with regular deposits. At the end of 4 years, Joe makes a one-off contribution of $10,000 and continues with regular quarterly contributions. We need to find the value of the annuity at the end of 6 years to the nearest dollar. So step one, we've just got to find the amount after 4 years and then kind of mentally pause, because then we're going to add 10,000 on. So because this is a relatively short-term investment, we've got 4 years compounding quarterly. We only have to find A16, which isn't too bad. We could use the annuity formula if we wanted to, but we could also use a recurrence relation exactly the same way. So using a recurrence relation, I can find out what R is by just doing 1 plus the interest rate as a decimal per compounding period. That gives me 1.009. The deposit amount per quarter is going to be 2,500, and therefore that is our recurrence relation. In this case, AO, the starting amount, would be 0 because we're starting from scratch. There's no initial amount. So because we want to find the amount at the end of 4 years and it's quarterly, 4 times 4 is 16. So we need to use this recurrence relation to find A16. So using the calculator trick, and if we keep continuing that pattern, we find that A16 is equal to this amount. Now what we want to do, step 2, is where we want to add on that $10,000 contribution to get the new total. So that means our new total at the end of 4 years is going to be $52,816.79. Now what we're going to do is we need to find the value of the annuity at the end of 6 years. Right now we're at the end of 4 years. So we've got 4 quarters in a year and we've got 2 more years, right? So we need to find A8 essentially from this point. So that's our new recurrence relation. Nothing's really changed except for AO. And then we're going to find A8. Once we use our recurrence relation to find A8, that's the value we get. And because we had to round off to the nearest dollar, the value of the annuity would be 77383. Next question, we've got TAM deposits a fixed amount at the end of each month into an account paying 8.6% compounding monthly. From an initial balance of zero, she accumulates $51,343.85 in 4 years. A financial planner has advised Tam that she would have been at least $3,000 better off if she had have instead deposited half of the fixed amount at the end of each fortnight into an account paying 7.9% compounding fortnightly. All right, there's a lot going on there. Let's just look at the first part. So the first part is long term and it's an annuity, right? Because she's depositing a fixed amount at the end of each month, and that's for 4 years compounding monthly, right? So 48 terms essentially. So I'm going to use the annuity formula here. So what we're going to have to do is let's just find out what her monthly deposit amount would be in order to have accumulated that amount in 4 years. So substituting everything into the formula, all of those things that we've substituted are just straight from the question. We need to rearrange and solve for m, so we're moving the entire big bracket over to the other side. Remember, we want to split this up into smaller parts when we're doing it in our calculator. So we're going to use the answer feature to help us, and eventually we get m is equal to 899.99. We can pretty much just round that up to $900. So therefore, this person must have been depositing $900 per month. So now let's read the second part. A financial planner has advised Tam that she would have been at least $3,000 better off. So she would have had $3,000 more if she instead deposited half of the fixed amount. So half of the fixed amount is $400 now. We've worked that out. So they're saying she would have been better off if she deposited half of the fixed amount at the end of each fortnight into an account paying 7.6% compounding fortnightly. Okay, so now what we have to do is we have to just use the annuity formula again with the new situation in orange and see what we would get all up. And then we're going to compare and see whether or not the new situation is at least $3,000 better off. So using the same annuity formula, substituting our values, all of those just come straight from the question. That 104 just comes from the fact that we're doing fortnightly for 4 years. And then when we plug all that into a calculator, we get that value there. Now notice the first option was this amount. So when we find the difference between those two, we get more than $3,000. So that means that the claim is reasonable. So the financial advisor's claim was correct, that she would have been at least $3,000 better off with the other investment option. Okay, next question. So 5 years ago, a retiree invested $100,000 in a compound interest account, earning 3.8% compounding monthly. Okay, they now intend to use the balance of the account to begin a perpetuity that will return 4% per annum compounding annually and pay them $6,000 each year. So we need to provide advice to the retiree about whether their compound interest investment is large enough to finance the perpetuity. So what we need to do here, we need to find out if the perpetuity is possible. To do that, we've got to find the total amount. And because it's just a regular compound interest loan, that's what we're going to use. And I've plugged in 100,000. I've plugged in my interest rate in blue, and then to the power of 60, because we've got 5 years compounding monthly. That gives us $120,888.66. Now what we're going to do is we're going to put that value into a perpetuity as the perpetuity amount, so as P. And we're just going to check if we did that, would we get $6,000 or would we get less than $6,000 per year? So we're going to use our perpetuity formula. I could say the payment amount is going to be the value of the perpetuity times by the interest rate as a decimal per compounding period. Because it's compounding annually, that's once per year, we can just write I as 0.04. So when we do that, I get $4,835.55. That's less than $6,000. So to answer the question, we had to provide advice to the retiree about whether their compound interest investment is large enough to finance the perpetuity. So it wouldn't be large enough because the perpetuity amount that we're going to get is less than $6,000. So we could say, therefore, the compound interest investment will not allow them to achieve this perpetuity. A larger amount needs to be invested to achieve this goal. So my solutions are a little bit different to what QCAA has done. I'd recommend checking out their solutions to all of these questions too. And that's it for this video, guys. Thank you for watching.